Welcome back. Before we get into the complex classification algorithm, we will go through the simple one, and in our case we will take the example of k nearest neighbor. Well, this classifier is a simple way to classify the data, and during the training it does nothing but just memorizing all the data and its level, and during the test stage or during the prediction stage we take new test data. In our case it will be image, and we try to find the most similar image in training data to that new test image. So now it predicts the level of that most similar image, like it will try to find the most similar image in the training data and label it it will categorize based on that similar training image. And let us see in a very in step by step let us see it in stepwise. In step 1 we start with the data set with the known categories, and here in this example the color indicates the data categories. And in next step what we do is we add a new data with the unknown category or unknown level, and what we want to do is we want to classify this new data or categorize this new data. And in next step what we do is we classify the new data by looking the nearest neighbors. And here before we go before we classify, first what we do is we have to set k. This value of k is nothing but the number of the nearest neighbors that it will test. So first let's see, like with k, with the value of k is equal to 1, and like when k is set to 1, then we only use the single nearest neighbor to this test to define the category. Here in our case, like in this case what we see is we take the only one nearest neighbor, and it will find the nearest neighbor pointed by the arrow, and it will label the its category based on the level of its nearest neighbor. Means the category or the label of this new data will be green. So we will classify this data as a green because it has found its nearest neighbor as a level of green. So now what we can do is we can increase the number of nearest neighbor. Like now what happens when k is equal to 5? Even in this case as well, the level of this new data will be green because all of its nearest neighbor are green. Like we can see here, all of its nearest neighbor are also green, so its level will be green. Now another example, let's see. So what happens when the data is somewhere between the between other colors or other categories? So in this case what we do is we simply pick the category that gets most votes, or first of all we will find the nearest neighbors, and based on that nearest neighbors we will take the we will try to find out the we will simply pick up the category that gets the most votes. Here what we have seen is like the green has there are 3 green and 1 orange and 1 blue. So the green got the most votes. Then we finally assign this data as a green level. So in this way we can categorize or we can classify the data. So another case is what happens if the new data is right between the two categories. Like in this case, if the value of k is odd, then we can just avoid lots of ties. Like there's no problem with the odd number of k's. But if still we have a tied vote, then we can flip a coin and decide not to, or we can flip a coin and we can decide any one of the level, or decide not to assign the data any category. So the way we find the nearest neighbor is using the distance metric or the similarity between the data. And there are two methods. There are basically we use two methods. One is the L1 distance, another one is the L2 distance. In L1 distance, what we do is we just take the modulus of difference and sum it up. And in case of Euclidean distance, what we do is we take the difference, we square it and sum it up and take the square root of that sum. So I think these are very familiar formula to us, so I don't need to describe it more. So when it comes to image, here is a simple example of the image. Like we have two images here on the left side and the right side. What we do is we just take the difference and take the modulus and sum it up, and finally we get the some value, and it will give us the similarity between two pixels, or two pixels. So based on this similarity, we can get, or based on this distance value, we will find out the k, which are the nearest neighbor to that unknown data. So now the question arises, how can we select the value of k, or the number of nearest neighbors to the testing data? So there is no particular way to determine the best value for k. So we need to try to some values to find the best out of them, and a very low value for k, such as k is equal to 1 or k is equal to 2, can be noisy, and it may lead to effects of outlier in the model. And similarly, the large values of k are good, but it may find some difficulties, or the complexity of the algorithm will rise. And let's see the strength and weakness of k-nearest neighbor. And when we talk about the advantage or the strength of the KNN, as we have seen that KNN algorithm is very simple, and we can understand it quite easily, and it can be implemented easily, and it's very simple to implement. And it has no assumptions. Like it's a non-parametric algorithm, which means there are no assumptions to be made to implement the KNN, and no training step. Like in case of training, we don't need to define a model, or we need to work for the model. KNN, like, it doesn't explicitly build any model, and it simply tags the new data entry based on the learning from the historical data. And like the new data entry would be tagged with the majority of class in the nearest neighbor. And the weakness of this KNN algorithm is it's very easy to implement, but dataset grows. As the dataset grows, efficiency or speed of the algorithm declines very fast. And another weakness is the cost of dimensionality, as KNN works well with a very small number of input variables, but as the number of variables grows, KNN algorithm struggles to predict the output of the new data point. And optimal number of neighbors. One of the biggest issues with the KNN is to choose the optimal number of neighbors to be considered while classifying the new data entry, like to specify the value of k. And it has also another problem of outlier sensitivity. Like the KNN algorithm is very sensitive to the outlier, as it simply chooses the neighbors based on the distance criteria. Like with the data with some outlier data, some data which are labeled wrongly, like with the different level, but at the very far distance cannot be classified correctly. Now another way of like this was about the KNN. Now we are going to discuss about the new way of defining the classifier, and the another way of describing the classifier is in terms of parametric model. Well, the parametric model comes with the two different components. It's gonna take in the image, which may be doc. In our case here we take the doc as input, and which is the image, and it's usually written as x. And another thing we consider is a set of parameters or weights, and which are usually written as w, or we can also be written as theta, but in our case we'll take here the w. And the classifier model can be summarized as a function of fxw, and that maps the input variable x to y. Here we have got the input x that maps to y. This y is the output variable, and these are, like here in our case we have the output variable will be two numbers giving the class scores, like we have taken the binary classification, so we'll have just two number of class, and this the output of the output value y is nothing but the class score which we get from this input. And then this will, based on that score, we will classify the categories, or we will this score correspond to the categories. Now if we look back on the KNN setup, there was no parameters. Instead we just keep around the training data, and the whole training set use that at the test time. But now in case of parametric approach, we are going to summarize the information or the knowledge of the training data in the here what we do is we are going to summarize the information or knowledge of the training data into these parameters w. And now at test time there is no longer need of the actual training data as it was needed in KNN classifier. We just use the w, or weights or parameters. With the help of this parameter w, we can predict the categories of the test data, so which makes the model more efficient. And here the form of the function is unknown. We don't know what will be the what is the form, or what is the how this function f is expressed. And the function comes from varieties of the form, ranging from simple linear regression to the complex deep learning models. And the different algorithms make different assumptions, and the combination of w and x and other biased terms which are about the form of the function, and we also don't know how it can be learned. So the formation of this function and the way it's learned, it varies or it depends on the classifier to classifier, or method to method. And if we look at the very simplest form of this combination of w and x, we can just write it as the product of w and x, or w times x. So we can add another term, also another term, this b, which we call the bias, and it is a constant vector. In our case here it will be the 2 element, and like it is used as a bias term. And this is the very simplest form of the parametric classifier, and just it is expressed by the linear equation. We can say it as a linear classifier. So let us see this function pictorially and what this function is doing. Let's see here. Like in this figure, we have example on the left of simple image, and we assume, it's just the assumption that we represent this picture of dog with the 4 pixels. Even though we have just discussed before, I've said before, like it was represented by 32 by 32 image, but just for the example here I have considered it as a 4 pixel of dog. And the way the linear classifier works is that we take this 2 by 2 image and we stretch it into a column vector with the 4 elements. Now it is stretched to the column vector, like these are the 4 pixels with 56, 2, 31, 24 and 2. And now in this example we are having 3 categories. Like we have got the 3 categories of cat, dog and tiger, and again we have 3 bias elements, and that vector, this is the vector that gives us the data independent like the bias terms for each category. And now for the category score, like the category score is going to be the inner product between the pixel of the image and the row of the weight matrix, and which is added together with the bias term, and this bias gives data independent scaling offset to each of the classes. In this way we can obtain the score for each category from the input image and the weight vector. Like this is the way of calculating the score. And now the question arises how the weight matrix is defined. Like we can see here, there are 2 unknown terms. One is the we know that this x, which is the input or pixel, we get from the input image, and we have here 2 unknown terms, 2 terms, weight and b. We don't know how it is specified here. So the question arises how the weight matrix and the bias are defined, and what gives us this weight, this weight that will precisely give us this score that matches the input image and the category. So we will do which we will be discussing in our succeeding classes, or in our next class we'll be discussing about how this weight or this bias values can be defined.